Hello, I'm Urania, the Greek muse of astronomy, and I'd like to help you with your revision of the astrophysics option in the AQA A-level physics specification. You may also find the following book useful: The A-level Astrophysics Workbook, by Dr. G.K. Fox, exclusively available in the Kindle store. It also happens to have a picture of me on the front. In this video I will review how to use Stephan's law. Stephan showed that for a black-body object, the power output per surface area depends only on the black-body temperature. It assumes that the star emits radiation uniformly over its surface, which is usually the case. It also assumes that the inverse square law of radiation is valid, which is usually the case, except when the radiation is in a collimated beam, or there is absorbing material between the observer and the star. Stephan's law is useful because, if we know the distance to a star, we can calculate the power output from its absolute magnitude. From its blackbody curve, we can determine its blackbody temperature. From Stephan's law we can determine the surface area, and, hence the radius of the star, which can only be directly determined for eclipsing binary stars. Here is an example question. Sirius is the brightest star in the night sky with an apparent magnitude of -1.5, it is only 2.6 parsecs away. Its spectrum can be approximated to a blackbody, with a peak intensity at 290 nanometers. Determine the radius of the star. You may assume the Sun has an absolute magnitude of +5, and a luminosity of 4 times 10 to the power of 26 watts. Here is a model answer. First we determine absolute magnitude of Sirius. We use the distance modulus equation. After substituting in the numbers and simplifying, we find the absolute magnitude to be +1.4. Second, we determine the luminosity. Sirius is 3.6 magnitudes brighter than the Sun. It is therefore 2.51 raised to the power of 3.6 times more luminous than the Sun, which is about 27 times more luminous than the Sun. This means Sirius has a luminosity of about 1.1 times 10 to the power of 28 watts. Third, we determine the blackbody temperature. From Wien's displacement law, with lambda max at 290 nanometers, we obtain a blackbody temperature of 10,000 Kelvin. Finally, we use Stephan's law to determine the radius. Substituting in the numbers from the previous calculations, we obtain a radius of 1.2 times 10 to the power of 9 meters, which is about 1.8 times the radius of the Sun. Thank you for watching.